We're going to be looking at circular motion now. So these types of problems are very well suited for the polar coordinate system. So I'll link down below my video all about polar coordinates. But for now, let's look at this particle. So here you have a particle traveling along a circular path. And whenever you see this condition, that's called circular motion. So the key thing here is our R is always going to be a constant, which makes sense because that keeps this traveling in a circle. So our velocity, now that we know our position, is going to be the same as what we defined in polar coordinates. So our velocity is going to be r dot times u sub r plus r theta dot u sub theta. But being that r is always a constant, that's going to mean that r dot equals 0 and r double dot equals 0, because taking the derivative of a constant will give you 0. So we can simplify this for circular motion to say that our velocity is going to be equal to r theta dot in the theta direction. And of course, our acceleration is going to be the derivative of the velocity with respect to time. And for polar coordinates, we defined our acceleration as r double dot minus r theta dot squared u sub r plus 2r dot theta dot plus r theta double dot u sub theta. And again, being that r dot and r double dot equals 0, we can abbreviate this to say A equals negative r theta dot squared u sub r plus r theta double dot u sub theta. So this can be our acceleration expression for circular motion. So being that our r component of the acceleration is negative, our acceleration in the r direction is going to be directed back towards the center, which will look like this. So this will be a sub r, and that'll be equal to negative r theta dot squared, which is the r component of our acceleration here. And our theta component is going to look like this, and that will be equal to r times theta double dot, which is again the theta component of our acceleration. And our velocity in the theta direction is going to look just like our acceleration, pointed the same. And our v sub theta is going to be equal to r theta dot, being that our direction, or our r component of the velocity, equals 0 because r dot equals 0. So let's look at an example. So a car is traveling along the circular curve of radius r equals 300 feet. At the instant shown, its angular rate of rotation is theta dot equals 0.4 radians per second, which is increasing at the rate of theta double dot equals 0.2 radians per second squared. Determine the magnitude of the car's velocity and acceleration at this instant. So if you want, you can pause the video here and use these equations that we have listed on the right, or you can keep watching and we're just going to try to solve it out. So we know from the problem, along with these equations, r is given to us as 300 feet, theta dot is given to us as 0.4 radians per second, and theta double dot is given to us as 0.2 radians per second squared. So looking at our velocity, So we know that velocity is going to be equal to r times theta dot e sub theta. So velocity in the theta is going to be this right here, and our velocity in the r direction is going to be equal to r dot, which equals 0. So 300 times our theta dot, this is going to give us our velocity in the theta direction. So that will work out to give us about 120 feet per second. And if we want to know the magnitude of the car's velocity, that's just the speed. So we're going to say the square root of the sum of the squares of the components of our velocity is going to give us the speed. So that'll be 0 squared in the r and 120 for our theta component. And that's going to just give us 120 feet per second is the magnitude of the velocity. And for acceleration, we have our expression here. So we can look at our r component and our theta component. So our r component is going to look like this, and our theta component will be this. So we can break this down. So we're going to say negative r, so negative 300 times our theta dot, which is 0.4. That will give us a value of negative 48 feet per second squared equals our r component of our acceleration. Now our theta component, that's going to give us r times theta double dot, so 300 times 0.2, and that will give us 60 feet per second squared. So the magnitude of the acceleration is going to be the same as above, so we're going to say A equals our r component and our theta component squared. So that'll be 48 squared plus 60 squared. So that will give us a value of 76.8 feet per second squared, which is the magnitude of the acceleration. Thank you for watching. If you like this video, please be sure to give it a thumbs up and subscribe. That really helps support my channel and helps me continue making videos for you guys. I'll see you next time.